Hi, in this video, we want to take a look at supervised learning models with imbalanced data. All right, so I'm in a situation where I have different levels of my target variable categorical data, and a level is lower than I want it to be. So let's say I have data, I go out, I include race and ethnicity in my sampling, and when I look at my sample data, I notice that the distribution of different races and ethnicities don't match my census data for the region that I sampled from. All right, well then I have to anticipate that I've got biasing going on in my data. All right, so we don't want that. We want things to reflect our true population that we want to know about. Also, another situation that we could be in is that, let's say I'm trying to model fraud. So let's say that, a bank gets a transaction for, somebody's getting a cup of coffee at Starbucks, something like that. And there's, the bank receives this, and very quickly, the bank needs to decide, are we going to release the funds for this? Because it might be a fraudulent, transaction. If it's fraudulent, stop, don't make the transaction. If it looks legit, send out the money. And there can be problems, either way. Send out, so if you make a mistake, on the fraudulent case, well, let's say you release the funds when it's a fraudulent case, then, somebody's out of money, either the bank or the account holder. Or let's say you don't release the funds. That you think it's fraudulent when it's not. This has happened to me in rural Georgia when I needed a hotel, that the bank thought I was making a fraudulent transaction, and now I don't have a place to stay because my card was locked out. Now, I was able to resolve it, but that's a problem. And so there's a problem with, there's some difficulties with modeling with imbalanced data. If you think about fraud, the vast majority of transactions are not fraudulent. And so proportionately, a fraction of a percent of the transactions are fraudulent. So that's not very much of a signal to base your model off of. Okay, so what we can do like tricks to increase proportionately the amount of data we have proportionately for that rare fraudulent level aspect. Now, something that we have to keep in mind when we do this, when I shift around my data, like I'm going to show in this video, when I shift around my data, my model is going to look like my training data no matter what. Your model always looks like your training data. All right, so let's say hypothetically, I took my fraudulent data and I used the techniques that we're about to use now, and I made it so that fraud was about 50% of my data and non-fraud was 50% also. Well, then the likelihood of let's say a 10% fraudulent case, that's actually pretty low because like 50-50 is our baseline. Now, if I was to go with the original data, and let's say that 1% of my data is fraudulent in my data set, then a probability of fraud of 10% would be huge. It would be 10 times the overall marginal, proportion. And so that's a huge, difference. While 10%, if I trained with a 50-50, would probably not be a fraudulent case. So we have to, consider this when we interpret our model afterwards. The probability of the level is going to reflect directly to the modeled probability. The modeled probabilities are going to directly reflect the training data that I give it. All right, so here's some examples of imbalanced data. So we have a classification problem where one or more levels is so rare that the level that is of really high interest just gets drowned out. Think about that fraud case. The vast majority of cases are not fraudulent. Another one is that a dependent variable does not reflect the known population distribution. So for this one, think about, I go out, I sample my data, And when I look at race and ethnicity, I see that my sample data is nowhere close to the census data for my area. Then I know there's a discrepancy. So when we talk about imbalanced data, it could be for a target variable or a predictor variable, or possibly both. Now here, we also have that the independent variables distribution in the sample does not reflect the known population distribution. And so if I have like subject matter experts, or if I have experience in my field, and I know what the proportion should, or the distribution should be, and then I look at my data and I don't see that, I need to correct that. I need to make some adjustments. All right, so here are the major ways that we can handle imbalanced data. There are other ones. These are the ones I'm going to talk about here. First and foremost is we want to adjust the weights of our observations to make them weight-wise reflect the distribution that we want. We can also do cost-sensitive learning. In this, what we do, we adjust our loss function in the fitting process to make certain mistakes, like bigger mistakes, and certain mistakes lesser mistakes, so that the model that we train gets really good at spotting what we want it to spot. Unfortunately, R does a pretty poor job of providing this as a feature, and so I'm not going to talk about it here. We can downsample our data. So in downsampling, what we're going to do is that I'm going to eliminate the high frequency level observations to balance out the data. So I'm going to take some of my data, and I'm not going to use it for training. I'm just going to basically just throw it to the side and not even consider it. Now, upsampling, what we're going to do is we're going to take the low frequency level of our data, and I'm going to put it in my data set multiple times to get that the overall distribution is where I want it to be. Now, another way is to create synthetic data. By far the most well-known one is SMOTE, but there's also ROSE. And another way is just to repeat low-frequency observations across our training, validation, and test sets. We don't like that because we can't trust our validation and test statistics when we do that. Oh, and our preference for this is the order that I presented here. Our number one preference is to adjust the weights of our observations. Second is to do downsampling. Third is to do upsampling. Fourth is synthetic data, in that order. Now, that's my opinion. Some people will disagree with me. I specifically don't like synthetic data because it looks like you're generating informative cases, but you're just basically doing some sleight of hand with your data instead of actually building new observations. It feels better than it is. All right, so here we're going to use the cover type data sets on this one, and I'm going to put all but the first two levels into an other category for this. And so this is a multinomial project, and I'm going to take the most common one is level 2. The second most common is level 1. All other types of cover, I'm going to put into the other bin. Also, I'm going to go through and do binary binning for soil type. I'm going to do binary binning for wilderness area, just to make things a little bit cleaner. I don't like having a lot of dummy variables floating around. Here I'm removing the columns that I use in the binary binning. Now, before I made the video, I did some exploration for boxcrocks, and I noticed that elevation squared would do better than elevation in terms of the boxcrocks transformation. The parameter was close to 2. So I'm squaring it here. And we're going to go through and do Yo-Johnson transformation on these predictor variables to try and improve our model performance. And we're going to partition our data into train, validation, and test sets. Here I'm doing approximately 1/3, 1/3, 1/3 on this. All right, and let's see. Yeah, I also did something with row names just to make things a little bit easier to track when I was working through it. All right, so now let's take the distribution of our target variable. All right, so when we do this, so here you can see the percentages. I've got about 15%, about 37%, and just under 50% here. So half of my observations are level 2, over a third is level 1, and then everything else, just about 15% is in the other category. And here, this shows the bar plot. All right, so my impression is that once we start seeing like a 2-to-1 ratio, it starts getting harder to pick up some of the features of the less frequency level. So if I have a 2-to-1 ratio, 3-to-1 ratio, 5-to-1, basically anytime I have a multiple of my, the largest percentage is a multiple, integer multiple or larger of the least frequency, we start seeing that things start getting drowned out. Now, you can still detect things, you can still do probabilities, you can still model very well, but I noticed that statistics starts like shifting and not being as reliable as possible. First one to really start degrading is the accuracy one. Consider the situation where I had 99% of level 1 and then 1% of level 2. Well, I'd achieve 99% accuracy just by saying level 1 every single time and accepting all the errors for level 2. That'd be 99% accurate, but that's not much of a model. All right, so as a benchmark, I'm just going to go through and I'm going to just run the model with the raw data as is. I'm not going to worry about the distribution of my levels for my target variable. And so what I anticipate is that my predicted values will probably look pretty close to this bar plot. All right, and I'm going to use the VGAM package for this. I'm going to use the multinomial. The VGAM package is very powerful, but it does take a long time to run. And I'm going to go ahead and use forward selection on the result just to get rid of any predictor variables that I don't want to have. And so here I get my model. Now, to address the imbalanced data, my first choice is to use adjusting weights. Here I get to take full advantage of all my entire data. This is a pretty easy technique to use. It doesn't take that much work. It's supported by a lot of functions. And so there's 2 ways to adjust weights. I can adjust the observations individually by row, or I can adjust by the different levels of the target variable. Both work very well. Not all functions allow us to adjust by different levels. The Ranger package, for example, does. Most of the time, you're going to be adjusting the weights of the observations. And a lot of functions in R, Python, Stata, whatever you name it, will do this for us. All right, and most functions allow custom weights. And now if you don't pass it a probability, most functions in R will go ahead and rescale the vector to be a probability vector. Now, it has to be a non-negative vector, so you can't have anything less than 0. Some functions won't accept 0, by the way, in R. It depends on the package. But it's best practice to go ahead and make sure that you have a probability vector for your weight to make sure it sums to 1 manually on your own. So for my resulting model, it's going to put more emphasis on avoiding training errors on the larger weight observations. But remember, weights are probability vectors. Increasing the weight of one observation decreases the weight of another. And so we have to strike a balance. Now, where is that balance? It's up to you to try and find that. Now, there's a misconception about adjusting weights. Adjusting weights will not improve the accuracy of your model. What it does is it changes where the mistakes are. So your model is going to try to avoid mistakes on larger weight observations. And so if I'm changing, if I have a high weight here, the model is going to put more emphasis on this one. but it's also going to sacrifice, emphasis over here. It's, think of it as a probability vector. If I put more emphasis here, I put less emphasis over here because they have to add up to 1 and it's non-negative. And so what we're doing when we adjust weights, we're controlling where the errors are. So adjusting weights actually will decrease my overall accuracy every single time compared to the unweighted training accuracy. All right, and we can also adjust the case weights real easily. And so here you can see that I went through and I've made it so that each of the cases have the same weight, the same amount of influence in the model. And so now when I build my model, I'm just going to use the case weights that I've created. And I'm going to get my model. And we'll look at all the models at the end together. Now we can also adjust class weights. Not very many functions in R give you this option, but basically the idea here is that I place an emphasis on different weights to get to adjust my package to have more emphasis where I want it to be. The Ranger package does this for us very nicely. Now the next technique that I have, so this is my second choice when I am working on imbalanced data, is to downsample that. When I say downsample, what I'm going to do, I'm going to filter out high frequency level observations, and that will balance out my data. So I've got, think about that, I've got the fraudulent cases, I've got the non-fraudulent cases. Well, what I could do here is say, hey, I'm just going to randomly select a bunch of non-fraudulent cases and just throw them to the side, not use them in my training model. All right, so what's nice about this is I'm going to have a smaller training set, so my computation time is going to be faster. That's going to be great. I can get through my project, easier. But it doesn't take full advantage of the data. I'm taking a portion of my data and I'm throwing it away effectively. And so those filtered data points are not part of the model. I may be missing something. Now in this code here, I am filtering out the data from the training set, but leaving the validation and test sets alone. And so here you can see that I've balanced out the data by filtering out rows of 2 and rows of 1. And so I'm using my downsampled data, and I just fit the model like I would regularly. Now, the next one that we want to look at is upsampling. Upsampling is I'm going to look at the low frequency level, and I'm going to repeat observations. Now, it's important to remember that if I do this repetition, if I put data points back into my data, I want to do this after I do my train test split aspect. If I put observations back in multiple times and then I do my split, I will likely have observations in different parts of the partition, and that will defeat the purpose of my validation and test statistics. And so what we're going to do when I do the upsampling, I'm going to do the upsampling on the training data only. So the upsample data has more observations than the original data that we started with. This takes full advantage of our data, but we need to be more careful that we want to do this on our training data only. We want to do it after we've done our train test split. And also, we're going to have some redundancy in our data, and that can honestly make some of our diagnostics, like our visualizations, look kind of wonky because I see the same observation appearing multiple times. Maybe they'll be stacked on top of each other, or maybe I'll have weird spikes in my visualizations. All right, and so here I'm upsampling, and you'll notice that so what I did was I left 2 alone, but then I sampled with replacement 1, sampled with replacement other, until I had exactly the same number of observations for all 3 levels. And then I build my model using my upsampled data. Now, the next way to go about this that I I like is to use synthetic data. So I'm going to generate fake data. So generating fake data it has all the pitfalls of imputation. So if I'm generating fake data, would that be a good idea if my model is going to be legally scrutinized? If my model was going to have to be used for, let's say, for like human resources, where I could potentially have a lawsuit challenging my model, I probably don't want to use fake data. That's something a lawyer could rip me apart for. I don't want that experience. So I would, avoid this. So, what I'm going to do for this is either I'm going to use Smote or Rose, more than likely. And so Smote, you can think of Smote as doing something like taking an average or a nearest neighbor's aspect to observations and using like the averaging of close points to create new data points. Now we're only going to do this on our minority classes, the classes I have fewer observations on. Now Rose, what this does is it's going to estimate the multivariate density of our data for the minority class and then use a random number generation to generate observations. And something I want to emphasize, and this is something I've encountered at work, is that Smote does, or synthetic data does not add new information. Basically, I'm just doing a sleight of hand with my data. I'm combining information I already have to have a different presentation. It's not new information. We're recycling information that's already there. I personally avoid Smote if I can. Sometimes when I have very, very little data, I still go with it. Smote is by far the most common way to approach this. And so here I ran Smote, and you can see what the proportions are here. So now other is actually greater than 1 and 2, kind of interesting. And I'm going to use my Smote data to go through and build my model. All right, so now let's compare predictions. So what I want you to see in particular is that when I change the distribution of my training data, I change the distribution of my predictions. So here, this is the original values. So I would expect to see something like, so here it's 52, 37, 12. This is what I would expect to see for the distribution if I just use the raw data. But I've changed the data that I use for fitting. And you'll notice for all of them, now the other category is more frequent and level 2 is less frequent. And let's see, level 1 is also more frequent. And so this has changed the distribution. If I had a particular distribution I wanted to have in the end, what I would want to do is I would want to make sure the data that I use for training has that distribution for the actual predicted values. All right, well, that's all I've got for you. Oh, okay, homework. For homework, I want you to go. I want you to take your data, get some imbalanced data somewhere, and use these 4 techniques and just check to see how does it change your distribution. And that's all I got for you. Life is short. Do math.